Swayam Prabha. Digital India. Educated India.
And I'll also illustrate this very simple way of doing this, which is, if you consider, let's take a flat surface, okay, and you have um, an interface like this, and we are making an angle. The local angle here is, let's say, is theta y. So let me basically the local angle is theta y, right? Now we have three surface energies. Let's call this as gamma. Then we have, this is gamma s, and finally we have gamma SL, solid liquid. Now what we will do is, we will take the surface and ask what would happen if the interface moves by a certain amount. So the interface originally was here, and I have to make sure that the angle remains the same. The interface originally was here, but now it has actually come to the new position here. My drawing skills are being tested here. That's the new position. So the angle has not changed, but the interface has moved by a distance of dx. And in the process, it has essentially, we have created an extra surface here, which is dx times cosine of theta y, right? This is theta y. The angle remains the same. Okay. Now, what we want to do is, we want to find out what is the work done moving the contact line by distance dx. Contact line by a distance dx. Now, if you want to write down this work done, we say this is simply dw is gamma solid minus gamma solid liquid times dx minus gamma cosine theta e d theta x. So this first quantity that you see here, this is basically the, because of contact line motion, because the surface, it has actually spread on the solid, right? It has spread on the solid, and then the second part that you see here is, it is from creating a new surface. Now the sign of this dw is not very important. That in other words, I could be moving left or right, the ultimately we want to find out if there is a small change in the position of the contact line and the interface moves on the surface, what is the work that needs to be done to move it, and provided the angle remains the same, right? So the angle, the sign does not matter because in equilibrium dw is 0, and if I do this, I get gamma s minus gamma sl essentially becomes gamma cos theta e, and therefore we get Young's law. Okay. Now this particular simple way of our analysis is slightly, it's definitely much simpler than, it looks definitely much simpler than the variational approach that we have taken, because it tells us that I can just move the contact line a bit and the interface a bit, and then ask what is the change in the work, what is the change in the energy or the work done, and hence find out the set that work done to 0 in mechanical equilibrium and get the Young's angle, right? So I think it's time to call it an end to this lecture, but let me illustrate what's going to come in the next lecture. So we now have looked at just a smooth surface. Now we want to look at wetting on textured surfaces. There are 3 kinds of textured surfaces that we'll be looking at. The first one is where you have a droplet that is sitting on a rough surface, and this is an idealized rough surface where you have a sawtooth pattern, but we'll see in the analysis that this idealization is not necessary. It could be an arbitrary rough surface, and the droplet, basically the liquid of the droplet, penetrates all the way into those little grooves that you see. You can have, when I say rough surface, the common thing that one may be accustomed to thinking about is a physical roughness. But if you're talking about only wetting, where surface energies are important, you can also have a situation where it's not really, it could be still a smooth surface, but it's not really a chemically homogeneous surface. Chemically homogeneous surface could be, an idealized chemically homogeneous surface could be illustrated as seen in the second figure. You have a droplet that is sitting on a checkerboard pattern where each square has a slightly different color. If you notice, they have different gray scales, and each of these squares actually has a different surface energy, and therefore the droplet is actually, when it is sitting on the surface, different parts of the surface is actually, different parts of the interface or the contact line are actually making contact with surfaces of different surface energies. So with that, how do we take this into account? This is a chemically heterogeneous surface. And finally, you can have a surface where the droplet is sitting on a surface, but it is not entirely making contact with the surface. It is also supported by tiny cushions of air pockets that you see. These air pockets also change the net energy of the system, and therefore this can manifest itself as different angles. Now notice that in all these 3 figures, I have not used the equilibrium angle as theta y. The angle that I'm using, the word equilibrium, because these are in equilibrium. These are droplets that are going nowhere, they're stationary. But the angle is not necessarily, the angle that we see is not necessarily the Young's angle, theta y, but it's a different angle. So I've called it as theta star. And what we want to do is, in the next lecture, is to come up with a relation between this theta star, the surface energies, and the roughness parameters. That's exactly what we're going to do in the next lecture. I'll see you around in the next lecture. Thank you.